So, welcome to the next lecture, and last time we were trying to find out what is the total power delivered by a synchronous generator whose terminal voltage is V 0 degree, and always draw the equivalent circuit like this here. This is EF and it is generator mode, that you also do not forget to write, and this is your impedance ZS, and then this is your terminal voltage V, and it delivers a current of IA bar. And this is how IA can be found out. You find out this voltage minus this voltage by ZS, this will give you current in this direction. And once you get that, the complex power delivered by the source is 3 V I star. We just did some complex algebra here to get this. Okay. Now, this of course, will be a complex number, and the real power, if you write like this, the power delivered by the generator, real and reactive power, I will say that Pg real power delivered will be the real part of this and this. So, you find out that 3 EF V EF by ZS, real part of this is cosine beta minus delta, very simple. Similarly, minus 3 V square by ZS, this is also cosine beta. So, real part of this and real part of this. Similarly, reactive power delivered, I will write QG, generator delivers this much reactive power, and it will be equal to 3 V EF by ZS, the sine components, imaginary part. So, this will be minus, sine of beta minus delta, and then minus 3 V square by ZS, and this will be also sine beta. Is that clear? So, this is the power, real power in watt, and this is the reactive power in VAR, volt ampere reactive, that is delivered by the generator. Okay. As a special case, if so, I am not sure whether you should remember this formula, because I do not remember. Anyway, for a numerical problem, it is better you calculate in this fashion, IA get whatever, how many formulas one will remember. But one thing is certain, one special formula is there that one should remember, that is a special case, when we say that RA can be neglected, If RA can be neglected, that means ZS, I am assuming it is ZX. And the reason for this I already told you, because of the fact armature resistance RA is much smaller than XS. So, that RA part if you neglect, it will be like this. In this case, then ZS become XS 90 degree, is not. So, I will put then for PG real power output will be equal to 3 V EF, ZS is XS, I will put like this, into cosine of beta is then 90 degree here. So, 90 degree minus delta, and then minus 3 V square by ZS into cosine 90, which will be 0, and this will be equal to 3 EF by V excess synchronous reactance into sin delta. That is the thing. This is one of the formula worth remembering. What it says that the real power with which we are interested, that is watt or kilowatt, how much power it is, or megawatt, how much it is delivering, the expression of that, it depends upon the excitation voltage, product of excitation voltage and terminal voltage divided by synchronous reactance, very easy to remember, into sin delta. And what is delta? In this case, for this particular case, how this phasor diagram will look like? It will be very simple, because in this case I have assumed your equivalent circuit to be EF, your ZS no RA. So, JXS synchronous reactance, and here is your V terminal voltage, and here is your load current IA. Are you getting? So, this is the thing V. So, in this case the phasor diagram will look like terminal voltage V, that is V 0 degree, and it is delivering suppose lagging power factor current IA. Load power factor is suppose theta, IA theta. Then to V no IARA, only thing IA JXS you have to add. So, drop a perpendicular here, extend this JXS into IA, it will be here 90 degree, and here is your EF. So, and here is the angle delta. In this case, of course, load angle, that V is delta. Therefore, the power delivered to the load depends upon the excitation voltage, product of excitation voltage, terminal voltage, all are per phase, divided by reactance in ohm into sin delta, where delta is this angle. Delta, as you know, is often called load angle. Sorry. So, this is the expression. Is that clear? So, this is the thing. Now, it is the real power, mind you, this real power whatever is delivering must be coming from the prime mover, whoever is driving this, is not. This kilowatt is the real power, okay. It is used by some consumers. Therefore, this much of power must be supplied by the prime mover. Prime mover, in which form energy is fed? If it is a steam turbine, we are burning coal. If it is water turbine, we are using some potential energy of the water resources. If it is diesel, we are burning diesel. The amount of coal needed to be burned now will become more the moment you start drawing power, extract power from the generator, okay, or more diesel is to be burned. So, the amount of real power supplied by the generator decides how much fuel is to be burned to deliver that amount of power. See, after all, it is a system where I am putting mechanical power and this one. So, this is similarly I can calculate QG, but this is most interesting formula. And this curve you can if you sketch it, it will be like this, a sine function. These are all for cylindrical rotor synchronous machines, cylindrical rotor synchronous generator. It will be something like this, a sine curve. This is delta and this is the real power Pg, okay. And this is P max, which is equal to 3 E f by into V by x s. Okay. Now, in general, when a machine is connected to the infinite bus, V is fixed, you do not have any control over V, terminal voltage. However, you can play with E f to increase the level of power. If you increase this P delta curve will be something like this. We will discuss this after some time, but this is the thing. Now, what is the torque axis? Torque is nothing but power. I know in this case there is no copper loss taking place, as if there is no loss in the armature circuit. Whatever power is outputted, that much power is drawn in from the mechanical side, and a balance operating point will be obtained somewhere here, is not? And speed is always constant. So, steady electromagnetic torque developed by the machine will be P g, and this is the torque in synchronous watt, you can say straight away. But if you divide by that 2 pi n s, where n s is in RPS, you will get the electromagnetic torque developed by the machine. And I will say the prime mover torque must be also same, but in the opposite direction. When the machine is operating under no load condition, operating point will be here 0. Go on increasing the load, the value of delta will come in. At this point it will operate here, at this point it will operate here, like that. Can it operate here? Suppose load is such that delta is this much. So, power and torque is synonymous in case of synchronous machine when you are considering steady state operation. Okay. Therefore, it is operating at this some delta at this point, suppose. Now, I find there are two operating points. You can easily show that this operating point will be not a stable operating point. Why? Because a slight disturbance around this point in delta, suppose rotor advances a bit, you will find that this is prime mover thing, prime mover torque. You will see it will the torque will decelerate the motor just like that, and it will come to stop. So, up to delta equal to 90 degree, this is the stable operating point. Like the induction motor I explained, it can be also explained in this. So, P delta curve is most important curve of a synchronous machine. Neglecting RA, it becomes much simpler like this, and between, so delta generally varies between 0 to 90 degree. Of course, so that it does not go near to the delta critical value, which is 90 degree, because if delta becomes more than 90 degree, it will enter into unstable zone, and you will not be able to operate the synchronous machine in the unstable zone. Therefore, delta must be in between 0 to 90 degree. Typical values of delta may be 10 degree, 5 degree, 20 degree. It should be in this linear zone preferably, and well below this unstable zone. So, anyway, this curve, P delta curve it is often called, is very much useful, P delta curve. Understood? Therefore, I will come to this curve slightly later once again if I have done the motor phasor diagram. But the fact is that a very simple expression of power delivered by the synchronous generator, if it is operating at some load angle delta, can be easily computed, provided you know the excitation voltage as well as the terminal voltage. Okay. Now, suppose I will just draw for generator operation, I will draw the Phasor diagram generator operation. When it delivers leading power factor load, okay. It will be like this. So, so how I am drawing generator plus minus, here is E f, here is your Z s. I will now draw for this whole thing Z s. This is R a plus J x s, and this is your terminal per phase voltage V, and I am saying it is delivering a leading current. Now, let us see how to draw Phasor diagram. So, this is V, and it is leading current. So, suppose this leading current with respect to V is this is I a. Follow me carefully, but this equation is true. E f is equal to your terminal voltage plus J I a into R a plus J x s, is not. So, this is what I will do. So, V plus I a R a I will add, this is small, and then to this I must add J I a x s such that this angle is 90 degree, and this length is much higher than this fellow. So, J I a x s, I am not breaking up J x a L and x a R, and then you will get E f. You see, this is this one is your V, green one, terminal voltage green, V and armature current. This is the power factor angle of the load that is there, and this angle between these two will be close to the delta E f, and because V will be equal to E r, we have seen. Acha, now, where is your phi f? Phi f is here. Perpendicular to this red line, here will be your phi f or M f or phi f, is not? This will be M f. And where is your resultant field? M f, this is the rotor field, mind you. M f is the rotor field which induces E f. Then M f plus your M a is along this line. So, M f plus M a, and this will be your M r, M resultant, because M r do not say it is resultant field. The notations I have used in case of synchronous machine is rotor field is E f, net field is M r, sometimes I am writing, but it is resultant field M r, because M f plus M a, this is M resultant. In which directions all the phasors are running? In this direction, suppose N s or omega s in electrical radian per second, all phasors are moving. In which direction electromagnetic torque is developed? It is the rotor field, it is advanced with respect to the resultant field. Therefore, electromagnetic torque must be this way, consistent in case of generator operation. Electromagnetic torque is in opposite direction of rotor. All phasors are moving with speed n s in this direction, and this is the thing. But in this case, you note one thing, this M f, it depends upon field current excitation. M f, length of M f will be less than M resultant, that is this one resultant, and then what should I call? I will call a generator operating at leading power factor must be under excited. Why under excited? Because field current decides MF, and that field MMF, rotor MMF, decided by rotor current decided by IF is less than M resultant. You can easily see if it is leading power factor, and therefore, it must be under excited. Therefore, we conclude that a synchronous machine operating as a generator, if it is delivering leading power factor load, then it will be operating as under excited mode. Under excitation, over excitation, the idea of that, if you have this complete Phasor diagram, you conclude that whether this rotor field MF compare the length of the rotor field and the resultant field. If the rotor field length is less than the resultant field, it must be under excited, we call it. In case of lagging power factor load, we have seen that it will be over excited. So, a synchronous generator, if it is over excited, it must be supplying a lagging power factor load. So, over excited synchronous generator, over excited, earlier we have seen that over excited synchronous generator supplies lagging power factor load, under excited synchronous generator will supply leading power factor load. Is that clear? Therefore, this is how this can be done. Now, what I will do, whatever time is left, that we will consider now a synchronous generator connected to infinite bus, means terminal voltage V is constant, I cannot change that, and late for simple understanding of the what is going on, the phenomena that I am going to discuss, it will be much easier, because after all RA is very small compared to XS. Therefore, ZS is equal to only JXS, pure reactance. So, under this condition, just this is the generator mode, this is plus minus EF, and here is your bus V, which is 0 degree, and it is delivering a current IA, and this is JXS, is not. And under this condition, we know power delivered by the generator, and this EF is EF delta. So, always take the terminal voltage which is constant as your reference. So, 0 degree. So, P is equal to, we have already seen, E f V by x s sin delta, very simple relationship. Okay. So, this is the thing, but it is also true this real into 3 per phase, it was like that. It is also true this thing is 3 E f, non E f, 3 V I A cos theta, is not. So, what I am telling is 3 E f V by x s into sin delta must be equal to also 3 V I A cos theta from the power factor of the load angle between V and I A. I could also calculate the real power output, and that must be same as this. Why not? The same quantities we have connected. So, it will be like this, of which you note that then it will be from both sides V goes and x s is constant. So, it will be E f sin delta by x s is equal to I A cos theta. X s and E f, suppose x s is constant. Suppose the machine is operating at lagging power factor, then I will draw it. Only one thing I will tell, and then today I will conclude. It is very, but get the idea. This is suppose terminal voltage I V. Suppose the generator is operating at some power factor angle theta 1, delivering a current of I A 1, is not. So, this is, and where is your E f? V plus j I A x 1, this will be your excitation E f 1, and what is the load angle? Delta 1. So, we have seen that E f by x s sin delta is equal to I A cos theta. Suppose the real power I am not going to change, because the I told you real power means how much fuel you are consuming. I am keeping that fixed, I will not allow it to change. It means that whatever real power I am pumping into this system, which is held constant, and I am not going to change that, which will ensure that output power is also constant. In this lossless machine, armature copper loss is also not there. Therefore, these conditions must be satisfied. Anyway, we will continue with this discussion next time, but please go through this derivation part on your own, this algebraic manipulation in this fashion. Very quickly you can do it. Use calculator, you can also try some numerical problems from your books, etc. Thank you.